Chapter 4 is on chemical reactions. This is a review of the three types of conversions we've discussed in Chapter 4. The first is if you are given moles of a substance and you are asked to convert to atoms or molecules of that substance, you need to know how to convert, and you would use Avogadro's number. If you are given moles of a substance and you are trying to find grams, you need to know how to convert that. And you can remember grams to moles, moles to grams, use molar mass. Or if you are given moles of one compound, let's call that compound A, and asked to find moles of compound B, a different compound, you would use the coefficients in your balanced equation. Now we will be combining the different types of conversions we have learned so far into multi-step problems. For example, if you are given the mass of substance A and asking for the mass of substance B, so from one compound to another compound, but instead of moles, you're given grams, or trying to find grams, we can look at kind of this overview of how you would solve for that. So if I'm given mass of A, I can go to moles of A using my molar mass. And if I have moles of substance A, I can go to moles of substance B using my coefficients, which is the equivalence from my balanced equation. And then from moles of B, I can go to grams or mass of B using the molar mass. And this is helpful because if you're working in a real lab, our scales again measure in grams, not in moles. So this is what's going to be more useful in the laboratory. This slide shows the same overview as the previous one. It has you starting with a plan. So if you're given grams of what you know, what's given, you can go to moles of what you know using molar mass. And once you have moles of what you know, you can go to moles of what you don't know using the coefficients in your balanced equation. And from moles of what you don't know, what you're trying to find, you can go to grams of what you don't know using the molar mass. Here are general procedures to do mass calculations. If you are given the mass of a specific compound and asked to find the mass of a different compound based on a chemical reaction. The first step will be to take the mass and convert to moles by multiplying by its molar mass. In this example, we want to make 345 grams of iron chloride. How many grams of hydrogen chloride will be needed based on this chemical reaction? We are going to assume that there is plenty of iron available. We start with our given, which is 345 grams of iron chloride. We're going to use the molar mass, which is given to us, to do the conversion. So we'll just set this up so that the units will cancel. So 162 grams of iron chloride is on the bottom of our fraction, and 1 mole of iron chloride is on the top. This way our grams of iron chloride cancel, and we end up with moles of FeCl3. So 345 divided by 162 is equal to 2.1296 moles. At this point, you don't need to reduce to the correct amount of significant figures because this is a multi-step problem. In step 2, we will multiply the moles from step 1. The moles from step 1 we calculated to be 2.1296 moles of FeCl3. We're going to multiply that by a fraction consisting of a coefficient of the compound whose mass is unknown divided by the coefficient of the compound whose mass is known. So the coefficient of the moles that is known is FeCl3. We have a coefficient of 2. The unknown, what we're looking for, is moles of HCl. So we will not be using iron or hydrogen coefficients. Using these coefficients, we can create our conversion factor. we want to set it up that the moles of FeCl3 will cancel. So we put 2 moles FeCl3 at the bottom, and at the top we'll put 6 moles HCl. That's what we're trying to find. This way our moles of iron chloride cancel, and we'll end up with moles of HCl. So 2.1296 times 6 divided by 2 is equal to 6.3888 moles of hydrogen chloride. Step 3 is to calculate the mass of the unknown compound by multiplying by the moles calculated in step 2 by the molar mass of the unknown compound. The moles calculated in step 2 was 6.3888 moles of HCl. So we need to get the molar mass of HCl. We use our periodic table to determine that. So we have the mass of hydrogen is 1.008 and the mass of chlorine is 35.45. So if we add those two numbers together, we get 36.458 grams is what 1 mole of HCl weighs. So we'll set up our problem. So we have 1 mole of HCl at the bottom, so we'll be able to cancel our units, and 36.458 grams of HCl at the top. So the moles of HCl cancel, and then we do our math. 6.3888 times 36.458 grams, and that gives us 232.926 grams. And this is the point in the final step where we want to do the correct amount of sig figs. So we were given 3 sig figs and 345, so our final answer should have 3. So it's 233 grams HCl. We want to make aluminum chloride by the following chemical reaction. Solid aluminum will react with chlorine gas to produce solid aluminum chloride. If we start with 350 grams of chlorine, how much aluminum chloride in grams can be produced by a complete reaction? We're assuming there is more than enough aluminum. The first thing is always to create a plan. You always start with what is given, which in this case is grams of chlorine, and what we're trying to find is grams of aluminum chloride. We can never go directly from grams of one compound to grams of a different compound. We always have to have that intermediate step of moles. So we can go from grams of chlorine to moles of chlorine, and then moles of chlorine to moles of aluminum chloride, and then moles of aluminum chloride to grams of aluminum chloride. So this we need to think about, again, how do we convert from one step to the next? So grams to moles use molar mass. So we need the molar mass of chlorine. And then moles of chlorine to moles of aluminum chloride, we'll use our coefficients from our balanced equation. Once we have moles of aluminum chloride, we can go to grams of aluminum chloride using the molar mass of aluminum chloride. So let's go ahead and get our molar masses of chlorine and aluminum chloride. So that's ready to go. We use our periodic table. So chlorine is 35.45 for 1 atom. We have Cl2, so we need to multiply that by 2. So we can do chlorine up here since we don't have very much room. 35.45 times 2 is equal to 70.90 grams per mole for chlorine. And then aluminum chloride, we have aluminum weighs 26.982, and then we're going to multiply or add that to 3 chlorines. So 1 aluminum, let's put this on the side here, 26.982 And then if we multiply 35.45 times 3, we get 106.35. Then we can add these two numbers together, and we have 133.332 grams per mole for aluminum chloride. So let's go ahead and solve the problem. We can have 350.0 grams of chlorine to start with. We're going to multiply that by its molar mass, which we calculated to be 70.90 grams per mole for chlorine. And then our grams of chlorine will cancel, and we'll get moles of chlorine. So that is equal to 4.9365 moles of chlorine. Our next step, we're right here, moles of chlorine to moles of aluminum chloride, we're going to use our balanced equation. So we go back to our balanced equation, and we have 3 moles of chlorine will produce 2 moles of aluminum chloride. And remember, we had plenty of aluminum, so we don't have to worry about aluminum at this point. So 3 moles of chlorine, we can write at the bottom of the fraction, and 2 moles of aluminum chloride will go at the top. So we can cancel moles of chlorine, and we can determine our moles of aluminum chloride. So 4.9365 times 2 divide by 3. That will give me 3.291 moles of aluminum chloride. I'm going to rewrite that number down here so we have a little bit more space. 3.291 moles of aluminum chloride. And now we need to convert moles to grams. We use the molar mass of aluminum chloride. So we know 1 mole of aluminum chloride weighs 133.332 grams. Now we can cancel moles of aluminum chloride, and then we multiply 3.291 times 133.332 grams, and we come up with 438.798 grams. Now we want to reduce to the correct amount of sig figs. In our problem, we have 350.0 grams of chlorine, so that is 4 sig figs. The final answer should have 4 sig figs. So we're going to drop some digits and round up. So our final answer is 438.8 grams of aluminum chloride. So that tells us if we start with 350 grams of chlorine, we undergo this reaction, we can produce 438.8 grams of aluminum chloride. And as I said earlier, this is really important in industry, because if you're a company that makes aluminum chloride and you have a customer that comes to you and says, I want you to make 438.8 grams of aluminum chloride, you need to know how much reactants you need to buy in order to make the product that your customer is desiring. So this is very important and something that's really useful in the real chemistry world. How many moles of carbon monoxide are produced from 36 grams of carbon in the following reaction? We're going to start with the plan, which always includes what are we given, which is 36.0 grams of carbon. And what we're looking for, in this case, what we're trying to find is moles of carbon monoxide. So let's go from grams of carbon to moles of carbon. And then from moles of carbon, we can convert to moles of carbon monoxide. And then we're finished. We don't have to go from moles of carbon monoxide to grams of carbon monoxide. That's not required because our question is only looking for moles of carbon monoxide. So with these type of problems, make sure you always make a plan and know where you start and where you need to end. So in this case, to go from grams of carbon to moles of carbon, we'll need the molar mass of carbon that we'll get from our periodic table. To go from moles of carbon to moles of carbon monoxide, we use our coefficients in our balanced equation. So we need to balance the equation that is given to us. We have Fe2O3 plus carbon producing Fe, which is iron and carbon monoxide. So if we look on the left in iron oxide, there are 2 irons, and on the right, we only have 1 iron. So let's put a 2 in front of that iron to balance our irons. Now oxygens in iron oxide, we have 3. So we can put a 3 in front of carbon monoxide, and now our oxygens would be balanced. And now we have 3 carbons in our product. So we need to put a 3 in front of the carbon in our reactants, and now we should have everything balanced. So let's go ahead and solve our problem. We'll go 36.0 grams of carbon times the molar mass of carbon from our periodic table is 1 mole of carbon weighs 12.011 grams. So I put my grams of carbon at the bottom of my fraction and the moles of carbon at the top. Now we could go ahead and solve the answer for here and get moles of carbon and then do our next conversion. But you can also do these problems in what I say a one-step setup. We can go ahead and say this would be moles of carbon. The next thing is to do moles of carbon monoxide. So let's set up our problem. To go from moles of carbon to moles of carbon monoxide, we need our coefficients in our balanced equation. So let's circle moles of carbon and moles of carbon monoxide. One we're trying to find, and one was the one we just calculated. So we can say there are 3 moles of carbon. We're writing that on the bottom to cancel our moles of carbon at the top here, and 3 moles of carbon monoxide at the top of our fraction. Now we can go ahead and see if our units cancel. Grams of carbon cancel, and moles of carbon will cancel, and we'll end up with moles of carbon monoxide. We can also see that a 3 divided by 3 will also cancel out from our mole ratio. And now we just have to do 36.0 divided by 12.011, and that will give us 2.997. And then we want to check our sig figs. We have 36.0 given to us. That is 3 sig figs. So our final answer should have 3. So we'll need to round this number up. This will be 3.00 moles of carbon monoxide that can be produced from 36 grams of carbon. How many grams of oxygen are produced from the decomposition of 7.35 moles of mercury 2 oxide in the following reaction? So with our plan, let's start with what's given, which is 7.35 moles HgO is mercury oxide. And we are trying to find grams of O2. So we need to figure out how we can go from moles to grams of 2 different compounds. So we can't go directly, so we're going to have to convert from moles of HgO to moles of oxygen. Once we have moles of oxygen, we can go to grams of oxygen. So to go from moles of HgO to moles of O2, again, we're converting from one compound to another one based on our balanced reaction. We need to have a balanced equation. We're going to use the coefficients from our balanced equation. And then moles of O2 to grams of O2 will be the molar mass of O2. So let's balance our equation. We can see on the left in mercury 2 oxide, our mercuries are balanced, however our oxygens are not. So let's put a 2 in the front. And when we change the 2 here, we need to balance a mercury on the right. So now we have a balanced equation. The other thing we said we needed in our plan is we'll need the molar mass of oxygen. So 1 oxygen is 15.99 and that's grams per 1 mole, but we have 2 oxygens in a molecule of oxygen, so we need to multiply that by 2, and that will give us 31.998 grams of oxygen per 1 mole. So now we can set up our problem. 7.35 moles HGO times, we're going to use the coefficients from our balanced equation. So we need moles of HGO and moles of oxygen. The mole ratio here, again, it's 2 moles. HGO is equivalent to 1 mole of oxygen. So we would write 2 moles HGO at the bottom and 1 mole of O2 at the top in our fraction. And again, we could solve here, or we can go ahead and continue with our problem and do this all in one step. I'm going to go ahead and do that. So on our molar mass, we would always put 1 mole of oxygen at the bottom to cancel our mole units, and 31.998 grams of oxygen at the top. Now you want to make sure your units cancel. Moles of mercury to oxide cancel, moles of oxygen cancel, and I will end up with an answer in grams of O2. So now it's just doing the math. 7.35 divided by 2 times 31.998, and that gives me 117.592 grams of oxygen. And in my problem, I was given 3 sig figs, so I need to have 3 sig figs in my final answer, and I'll need to round up, so that's a 118 grams of oxygen that can be produced from 7.35 moles of mercury 2 oxide. Percent yield is a formula you want to remember. Percent yield is actual yield divided by theoretical yield times 100 to make it a percent. What actual yield is if you were to make a chemical in the laboratory, it's the actual quantity of product that you produced in the lab. Versus theoretical yield, this is the quantity in theory of a product produced in a chemical reaction. This would be the answer obtained from doing mass calculations like what we're doing in this lecture. So this is what we've been writing down on a piece of paper. We react these chemicals. This is how much we can produce. In a real lab, you don't usually always produce the quantity that you think you can. So for example, I used to work at a pharmaceutical company, and our goal was to have a 97% yield. So we knew on our process of making the pharmaceuticals that we couldn't get 100% yield. That's your objective, is if you got 100% yield, that's wonderful. We knew we could make 97% yields because in the process you lost some of your reactants along the way. Maybe they stuck to the container you were mixing them in. So if a customer requested a certain amount of a product, we always knew we needed to make a little bit more because in our process we were going to lose a little bit. So percent yield is used in the real world. What is the percent yield of popped popcorn? When you make popcorn, you start with these popcorn kernels. So I have started here with 7 kernels. When I add heat to my kernels and pop them, I, in theory, could produce 7 pieces of popcorn. So my theoretical yield is 7. Let's see when I apply heat how much popcorn I can make. Okay, so it looks like 5 of my popcorns popped and then 2 of them didn't pop. This is usually what happens to me at home. I can never get all of those kernels to pop. So my 5 that popped would be my actual yield, what I actually produced, because 2 of them didn't pop. So to calculate my percent yield, it's actual over theoretical. And one student told me how they remember percent yield as PAT, because sometimes the only thing a student might get confused on is the actual over the theoretical. They might sometimes put theoretical over actual. They remember PAT, P is the percent, A is the actual, and that comes first, so that's the one at the top, and then theoretical is at the bottom. So our percent yield would be 5 divided by 7. To make it a percent, we multiply by 100. So I end up coming up with 71% yield for my popcorn. Based on the following reaction, if we start with 350 grams of chlorine, the theoretical yield of aluminum chloride produced is 438.8 grams. So we looked at this earlier. We had aluminum reacting with chlorine, producing aluminum chloride. And we produced 438.8 grams. We calculated that on the piece of paper. That was our theoretical yield. If the student went into the lab, the actual yield they obtained was 398.2 grams of aluminum chloride. The question is, what is the percent yield? So the thing to remember with percent yield is it's actual over theoretical times 100. So the actual yield was 398.2, what the student produced in the lab, divided by theoretical, which you would have to calculate out based on the amount of reactants you started with. It's 438.8 grams. Then you multiply that by 100, and you would come up with 90.74749%. And then you always want to do significant figures for any type of calculation, so percent included. So when we have 350 and 438.8, they both have 4 sig figs. So my final answer should have 4 sig figs. So let's go ahead and drop some digits and round up. 90.75%. How many grams of glucose are produced in theory from 3.75 grams of carbon dioxide? That's our first question. The second question is, what is the percent yield if 2.2 grams of glucose is actually produced? So let's start with the plan for the first question. So let's write our plan here. We're going to start with what is given, which is 3.7 grams of CO2. What we are trying to find is grams of glucose, which is C6H12O6. So we need to make our plan. We have grams of one compound, we're going to grams of a different compound. We cannot go directly. We need to find our intermediate step, which is the mole. So moles of CO2, we can convert to moles of glucose, C6H12O6, and then to grams of what we're looking for. So again, grams to moles, we use molar mass of CO2. Moles of one compound to moles of another one, we use the coefficient in our balanced equation. And then moles of glucose to grams of glucose, we use the molar mass, which is given to us in the problem. Okay, so we're going to need to calculate the molar mass of carbon dioxide. We can use our periodic table, and we see carbon weighs 12.011, and oxygen weighs 15.999. There's 2, so we multiply that by 2, and that gives us 31.998. So we add that to 12.011, and we come up with 44.009 grams per mole for CO2. The other thing we're going to need to do when we convert from moles of carbon dioxide to moles of glucose, we need the coefficients from our balanced equation. And our equation is not balanced here. So we can see on the left we have 1 carbon, on the right we have 6. We can put a coefficient of 6 here. And on the left in water we have 2 hydrogens. On the right in glucose we have 12. So we can put a coefficient of 6 in front of the water. Now our hydrogens and carbons are balanced. We need to balance oxygen. So on the left, we have 6 times 2, 12 oxygens in our carbon dioxide. And we have 6 times 1 oxygen here. Gives me 6 oxygens in the water. So total we have on the left is 18 oxygens. On the right, in glucose, we have 6 oxygens. And in order to get 18, if we put a 6 in front of O2, that will give us 12 oxygens, and 12 plus 6 gives me 18 oxygens. So we have a balanced equation. So now we can go ahead and solve our problem. So we have 3.75 grams of CO2. We said we're going to use our molar mass to convert to moles. So we can say 1 mole of CO2 weighs 44.009 grams. And then the next step is going from moles of CO2 to moles of glucose. So we're going to refer back to our balanced equation. 6 moles of CO2 will produce 1 mole of glucose. So 6 moles of CO2, I'm going to write at the bottom of the fraction, and 1 mole C6H12O6 at the top of my fraction. Now I'm going from moles of glucose to grams of glucose. I'm going to use the molar mass, which was given in the problem. And that says 1 mole of C6H12O6 weighs 180.16 grams. And again, that's of our glucose. So now let's check that units cancel. Grams of CO2 cancels grams of CO2. Moles of CO2 cancels moles of CO2. Moles of glucose cancels moles of glucose. We end up with grams of glucose, which is what we want. Now we can just do our math. 3.75 divided by 44.009 divided by 6 times 180.116, and that comes out to be 2.5856 grams. And we always want to check our sig figs. We started with 3 sig figs. So my final answer should have 3 sig figs. So let's call that 2.56 grams of glucose, C6H12O6. Question 1, done. We know the grams of glucose that can be produced in theory from our grams of carbon dioxide. The second question is, what is the percent yield if we actually made 2.20 grams of glucose? So then we go to our percent yield formula, which is actual divided by theoretical. So actual is 2.20 grams. Theoretical, we calculated, is 2.56 grams. We're going to multiply by 100. And I have 85.9375. And again, I want to convert that to the correct amount of sig figs. I'm given 3 sig figs for actual and theoretical. So let's reduce that to 85.9% for the percent yield for the amount of glucose.